Okay, so this is just a very short, quick revision of the main hypothesis test that I'm going to be putting on the exam. I've kind of done it in the context of the videos I did to support the homework and the class material, but I'm just going to try and keep the things brief. Basically, in the exam, I'm going to ask you about the hypotheses. I'm going to ask you how to interpret the results. And the interpretation will be based on the p-values. Good reason for this. The use of the p-values is constant across all the different tests. And it's probably the most useful thing in practice. If you're viewing computational results, you're not going to be messing around looking up at statistical tables. You're just going to be focusing on the p-values. So let's just kind of work out where my whiteboard is. So the tests we're going to do are going to be the single sample t-test. Now again, the book also, and in the homework examples, we also had like a single sample z-test, but for the purpose of, you know, the examples, we're going to, in the exam, I've kind of stuck with the t. Regards, t is the sample version where we don't necessarily, where need the kind of the population standard deviation. So we kind of have x bar, s, and n, and we're trying to make inference on the population mean mu. And we'll be looking at the two sample t-test. And here is basically the same. We have x bar 1, s1, n1, and x bar 2, s2, and n2. And we're making inference on the difference between two means, mu1 and mu2. Then we're going to look at a single sample test of proportions. And this is a z-test. So this is a z-test. And here we have, the x, the number of successes. Did I spell successes right? I don't know. Then we have the number of trials. And then we have our p hat, which is our x over n. And this is we're making inference on the population value p, the population proportion. Let's see if I can move this up a little bit. Switch back to the pen. Then number 4. Yikes. We're looking at ANOVA. And here we have inference on like multiple groups. We're not explicitly calculating the means, but basically we're looking at the hypothesis. We're looking at multiple means. So for example, we might have, if we have k-means, we'll be making inference on mu1, mu2, all the way up to mu-k. And then finally, we have our chi-squared test of association. Where we basically looking for association, we have two categorical variables. For example, we could have gender, male, female, and other, and brand awareness. So we're seeing an association between gender and whether somebody's aware of a brand. We're maybe a cell phone gaming company. We're worried that females are less aware than males. So brand awareness, yes and no. So all I'm going to do is for each of these little examples, and I just, because I mean this chapter throws a huge amount of statistical tests, and I know a lot of you took the prerequisite to class the semester before, but in reality this chapter is just, you know, kind of letting you do some of these tests in Excel, and also kind of sets up some of the work in other chapters. So I've just focused on these particular tests. So there are some other tests. For the 1 and 2 sample tests, we could have z-tests where we kind of assume or we estimate the population standard deviation. We also have a test of variances, which we might want to use to determine which 2 sample t-tests to use. And we also have the multinomial kind of chi-squared goodness of fit. But these are kind of the core tests that I'm including on the exam. And all I'm going to do now is just go through the examples we had in the videos, but just kind of quickly, just make sure you know the null and alternate hypothesis and how to interpret the results, pretty much just using p-values. Okay, so first up, it's the single sample test. And we had a couple of examples on the videos. I'm just going to do the first one, which was a vacation survey. So let's just snip this screen so I can write on it. Okay, and I'm going to write on it with, what color pen shall I have? Let's just have the red pen. So what we have here is we have some data. Now notice single sample will kind of have one column of information that's useful, which we're going to use. We have some other information here, but we're not using it in the test. So basically, we've got some sort of survey, and we're recording the ages, and we want to know if the average age is the same or different from 35. So we're just trying to work out from, we have our sample of the population of people who maybe go on certain types of vacations, and we want to know whether the population, the average age is different from 35. Maybe we're worried we're not attracting the youth to our holidays or something like that as a business justification. So the null hypothesis here is that the mean is equal to mu0, which is our hypothesized value. And again, for simplicity, I'm sticking, and in the exam as well, I'm sticking a stick with the two-tail version. H1, the alternative hypothesis, is that the mu is not equal to mu0. And of course here, our hypothesized value is 35, so we could write this as mu equals 35, and mu is not equal to 35. Now, we run our test statistic, we've got the two-tailed here, and we have a few important things. We have our actual t-statistic, but more importantly for the exam, we have the p-value. We also, of course, have the critical t-statistic. So let me just draw a little distribution here. I have to be quite small. And so we have our rejection region at the edge. And that's basically, we can see our critical value is 2.03. So this would be minus 2.03, 2.03. And so we're going to reject if the absolute value of t is greater than 2.03. But we're also going to reject if the p-value is less than alpha. So the p-value, let's just get a different color. Let's get blue. So the p-value here, so our actual t-statistic 2.72 is in the rejection region. And our actual the red area is the alpha, our p-value is here. So the red is the alpha and the sorry, the blue is the p-value. So the blue is the p-value. And the red area here is our alpha, which is 0.05. The levels of significance are always kind of based on probabilities. So we see 0.05, our p-value is less. So what we could do is we could say we're going to reject H0 as we could actually do as my absolute value of the t was greater than 2.03, which it is because it's 2.73, but we're going to be simple. It as p equals 0.0101, which is less than 0.05, which is our level of significance. So key here, you've got your level of significance, you have your p-value is less than the level of significance, so I reject H0. So my conclusion is, and we're positive here, the sample mean is 38, and we're testing 35. So I have evidence that the sample mean is different from 35, and based on my data values, we think it's probably going to be somewhere greater than 35. Okay, so that's the first little example, and I'll just pause it and then go on to the two sample bit. Okay, so next up is the two sample test. And what we have here, this is our friend which we keep coming back to, the purchase order database, the data, and we have alum sheeting and durable products, and we have an order lead time for each of these. And we want to see if there's a difference between order lead times in the products. We want to know if the difference from alum sheeting and durable products. So let's get my little red pen. So the null hypothesis, and you can see here, this is like set up a little bit differently. Usually we'd have these in two different columns, but our data here for alum sheeting is here, and our dating here for durable products is here. Okay, so we want to know if there's a difference between the two means. And so this would be our null hypothesis. Another way of writing it would be and our two-tailed alternative hypothesis. Now, you have to forgive me when I keep trying to write A instead of 1. Literally every other textbook I've ever used has always used A. So I keep trying to do that. It's kind of muscle memory. So the alternative hypothesis is mu1 minus mu2 is not equal to 0, or mu1 is not equal to mu2. And if you do the simple algebra, bring mu2 to the side, you'll see they're exactly the same. So again, we're going to do the t-test. And let's just have our little distribution here with z, basically the 0 in the middle. And the idea, again, is we've got this null hypothesis distribution. And when we calculate the t-statistic, we basically have this distribution with a mean of 0 and standard deviation of 1. Now we have two different tests here. We have assumed the equal variances and unequal variances. For large sample sizes, these are usually pretty much identical. The other thing to note, if we have these small sample sizes, we're kind of assuming that our underlying data are normal. For large sample sizes, it doesn't really matter as much based on this thing called the central limit theorem. Anyway, focusing on the exam, you'd need to know the null hypotheses. And again, it's very similar. Let's just kind of, we can actually do, this isn't on the exam, but we could have done an F-test for equal variances to determine which one to use to determine whether we have equal variances or not. But don't worry about that. So let's just assume that we're doing the unequal variance version. Oh, God. Actually, that's been knocked off the bottom. So we're going to assume the equal variance version. So our alpha here is going to be 0.01. So we've got a relatively strict test. If we've got a two-sample test, this alpha is divided between 2. Sorry, if you've got a two-tailed test, the alpha is divided by 2. And it's 0.01. And we're going to reject H0 if, as before, my t is greater or than t alpha over 2, or basically all you really need to know is that the p is less than the alpha. So my critical two-tail, which is the important thing because we're focusing on the two-tail, is 2.86, and my actual t statistic is 4.4. So we'd say that the 4.4 is greater than 2.86, so we reject. Or let's get my blue, let's just keep consistent. For my p-value, it's this incredible 0.00003. And remember, the two-tailed p-values are kind of on either side. This in total is 0.03. So p equals 0.0003, which is less than our alpha 0.01. So again, we reject. And again, it's always easier to just do the p-value because that's the same for every test. So we did the hypotheses. We look at the results. We've got our t statistic. Then we look at the critical two-tailed t and the two-tailed p-value. Our t is greater than the critical t. Our p-value is less than the alpha. So because of both of that, we reject. So there we go. That's the two-sample test. So let me just pause, and then I will move on to the next. Okay, so here we have our test for proportions, and let's just do our usual snip and remove our previous snip. And so we have our test for proportions here. Now, a few things to note with this. Let's move back to red. We don't actually have much data this time. All we get for a test of proportions is we have our sample size, our n, and then we get either the number of successes or our actual sample proportion as opposed to our hypothesized value. But let's just start with our hypothesized value. So we have some software company here. So let's just assume we're thinking about the number of people who renew their contract. And we want the number of people to renew their contract to be 75%. So 75% of the people renew the contract. And so in this instance, our null hypothesis, remember, this is p, not mu. We're looking at the proportion. So this is like a simple sample test, but the proportion is 0.75. The alternative hypothesis, and I got the 1, not the a, first time this time, is not equal to 0.75. Now, our actual data, we would usually have the n, which in this case is 44. We'd have the number of successes, which in this case is we don't tell us, but we have our p hat, which is x over n, which in this case is 0.7955. So we've been given the sample proportion, so we don't actually have to calculate this. It's been given to us. So we kind of know already this proportion is actually greater than 0.75, but is it statistically significant? Does it give us enough evidence to reject the null hypothesis? So we do this is going to be a z-test using the normal distribution. And we've got our alpha is 0.05. Here we go. So that's how strict the test is. So we're going to reject H0. We're going to, again, for this exam, I'm just going to focus on, so much was kind of revised in this chapter, thrown in this chapter. We're just going to stick with the two-tailed t-test. If the absolute value of z is greater than z alpha over 2, which is 0.25, and this is going to be 1.96. But again, we also reject H0 if my p is less than alpha. Now, my actual z here is 0.6963. So z equals 0.6963, which is less than or equal to 1.96. And I'll stick the absolute value here. So we're going to fail to reject H0. And again, my p-value up. I need to draw my p-value here. So let's just draw it a little bit up here. So we have plus 1.96, minus 1.96. We have our 0. And then we have our alpha over 2. And my z was literally about 0.69. And literally my p-value, remember the p-value goes on both sides. So my p-value is all of this from 0.69 to minus 0.69. Let's just, I was going to try and, let's just draw it. Let's just draw it down here. So we've got minus 0.69 plus 0.69. And the p-value is basically the area. More extreme than that, which is a lot bigger than the actual alpha. So we can also say that p equals 0.486, which is greater or equal to my alpha 0.05. So fail to reject. So again, this is you've kind of see the pattern here. We reject if the absolute value of our test statistic is bigger than the critical value, in this case 1.96. And we reject the p-value if it's less than the alpha. So in this case, z 0.6963 is not greater than the absolute value. That's not greater than 1.96. So we fail to reject. P-value of, where are we, 0.486 is greater or equal to 0.05. It's not less than alpha. So again, we fail to reject. So again, exactly the same principle on all of these tests. And let's just pause Camtasia. Okay, so on to Anne over here. So let's just clip the full screen. Okay, so we have 3 groups. We have college graduate, graduate degree, and some college. And we have some sort of a satisfaction rating for our service, whatever it is. I'm guessing it's kind of some sort of insurance, given the words premium and deductible. We want to know if there's difference in satisfaction between college graduates, graduate degrees, and some colleges. So literally we have, let's go back to red. We have 3 means, mu1, mu2, and mu3. And you could actually see we have the sample means calculated here. And, you know, looking at this, we could see that group 2 is obviously the highest, then group 1, followed by group 3. But, is this statistically significant? So, for the ANOVA, our null hypothesis is all means are equal, and H1, at least 2 means differ. And that's kind of always the same. So we don't need to reject the null hypothesis. We'll still reject the null hypothesis if mu1 and mu2 are equal, but mu3 is different. Just one mean has to be different from one of the means. So one, at least, has to differ a little bit. And basically, if I was doing this and I had a whole semester to teach statistics, we'd build this up really methodically with this ANOVA table, and I'd have you calculate all these things and then fill in the ANOVA table. But you're lucky to escape all of that. So we have the F distribution, and we're only focused on one side of this where we have the alpha, and we're going to reject H0 if F is greater than F alpha, and then we have the degrees of freedom here, basically the numerator and the denominator. We're not really worrying about the F statistic. So this would be 2 and 21 degrees of freedom, but this isn't going to be on the exam. I think we've chosen 0.05 here. But again, we also reject H0 if my P is less than my alpha. So let's just have a look what my F critical is. It's 3.4668. Now, let's go to my blue. Let's go to my blue. So my actual, if you look at the table you get from Excel, you have your critical value, which you're trying to get greater than. You have your actual F value. So we can see here that F is 3.92, which is up here. So this is a little bit squashed, but it's kind of greater than my critical F value. So we can say that my F is greater than F crit. So reject H0. And we're checking my alpha here is 0.05. And we also have my p-value. And we can say that my p-value, which is 0.0356, is less than my alpha, which is 0.05. So again, reject H0. If we had a stricter test, and again, we're to the right, so this is my p-value here, which is less than my alpha. If we had a stricter test of 0.01, then we'd fail to reject. So what we can say is at least 2 of these groups differ. And I think, as I've said in my full videos, if I was to tell that to my boss, they'd go, God, two means differ, but I don't know which 2 means. My boss should tell me, oh, you're an idiot. But for the purpose of the exam, just worry about this hypothesis. Kind of as a business application, once you've done this test, then you really have to work out, which means differ. But purely this test, P is less than my alpha, reject. F is greater than the F critical, so reject. Okay, so the final little example is the chi-squared example. Now, actually, the video I did for this, I spent a lot of detail going in how we built up these, both the contingency table and the expected contingency table. So for detail, go back to that video. Again, I'm going to be relatively succinct here as we're covering all of the tests. So let's do a full screen snip. So we have, and this, I guess we're a little bit out of date here, but this is the data set we got. We have, from the book, we have 3 brands, and we have female and male, and we want to see if there's an association between brand preference for these 3 brands and gender. Doesn't tell us what domain this is, but this is kind of a very simple marketing example. So let's just think of our categorical variables. We have gender. No, let's go. Let's be consistent. Let's go. We have gender, and we have brand. And this test is the test of association. So we'd say that gender and brand are independent, and H1, gender are dependent. Now, the statistic is the chi-squared statistic. We have, and again, you want to refer back to my specific chi-squared video, but this is, we have a significant value, we have a calculated value. Let's just draw the chi-squared. It's like the F, but it's like a mutant between the F and the normal. And in fact, it's actually a squared Z distribution. So we have our alpha here, and then we have our chi-squared, the critical value, which for this would be with 0.05. And we have a degrees of freedom, which is k minus 1. So it's the number of rows minus 1 times the number of columns minus 1. So in this case, it's 2 minus 1, 1. 3 minus 1 is 2, so it has 2 degrees of freedom. This would be 5.99. So again, for the exam, if I ask this question, I'd focus on the p-value. So we're going to reject H0 if chi-squared is greater than 5.99, or if the p-value is less than alpha. Now, in fact, the chi-squared, we have it here, is 6.49, which is greater than 5.99, so we reject H0. So we have evidence that the gender and brand are dependent, but we could do it the other way. In that we see here that my p-value is 0.0389. So here we are, this was like 6.49. And we've got the p-value here, 0.0389. So we're going to reject if p-value is less than alpha 0.05. And in fact, my p-value is 0.0389, is less than 0.05. So we're going to reject H0. So again, there's evidence that gender and brand are dependent. And let's just go back here and say chi-squared is 6.5, so reject H0, just to be consistent. Okay, so those are the tests, and this was really just to help you. This is like a summary of the summary videos I did, and it's really just in the exam I'm focusing on, do you know the hypotheses, and do you know how to accept and reject, particularly based on a p-value. So hopefully these videos have shown you that.